Now the next term, which is also very important to explain electric current, that is means current not only depends on all these things, but it also depends on a term that is known as drift velocity or drift speed. If we take magnitude, then we will call it as speed. So drift speed or drift velocity. One thing we have to again remember, in case of current I, this current I does not depend on, if we use a same conductor and if that conductor is having different area of cross section, then for same conductor, you may notice that the value of current I does not depend on the area of cross section, whether it is large or small. For a given conductor and for applied given potential, value of current remains constant, means it does not depend on area of cross section. Similarly, now we have to think about this drift speed or drift velocity. Drift velocity means when we apply electric field to this conductor, field is applied from positive to negative, and all these free electrons are moving towards this positive charge, means all these are get drifted towards positive terminal. So the speed is taken in the direction opposite to applied field. But first of all, we have to define what is mean by drift velocity or drift speed. So drift speed is nothing but, or drift velocity is nothing but average velocity or speed of free electrons when field is applied which causes electric current. This drift velocity or speed is denoted by letter Vd. Means when you apply this electric field to this conductor, all these free electrons gain certain amount of energy, so all these are get dragged in one direction, and during this direction they may collide with each other or collide with the vibrating atoms, and so these drifted electrons are having minimum velocity, and that minimum average velocity is known as drift speed or drift velocity. Most of in conductors 10 to the power -4, this much is a very small speed of these drifted electrons. Now we have to write relation for drift speed or drift velocity. As we know that these electrons, due to the application of this electric field E, that means here V is a potential, and these electrons are now moving with velocity Vd towards this positive terminal. So motion of these electrons through this area of cross section A in time, unit time, can be written as here I have written the relation for current, that is I is equal to, if number of electrons, that is N into E is a total charge area moving through area of cross section A with velocity Vd. So this is relation for current, and from that relation we can write the relation for drift speed. The basic first relation for drift speed is as Vd is equal to current divided by N into E into A. So this is equation number 1, which represents drift speed. Now the another relation for drift speed can be written as we know that current upon area is nothing but current density. So drift speed Vd can be written as Vd is equal to, here we can write J divided by N into E. But we know that this current density is always related with this electric field by relation as J is equal to sigma into E. So put this value of J in above equation, you will get Vd is equal to sigma into E divided by N into E. So this will be second and this will be the third relation. But we know that this sigma is nothing but reciprocal of resistivity, and so another formula you will get for drift speed as Vd is equal to E divided by N E into rho. But according to definition or in electrostatics, we have derived the relation between electric field E and potential V. If it is across a length or through a length L, then there is a relation between E, V and L as E is equal to V by L. That is, electric intensity is always a potential gradient. So drift speed can be written as Vd is equal to, here right, V divided by N E rho into L, and this is, I think, fifth relation for drift speed. So drift speed or drift velocity depends on all these things. One by one we think this drift speed basically depends on area of cross section, and from all these relations we finally conclude that this drift speed is inversely proportional to area of cross section. But for this condition we have to remember that if we use a conductor and that conductor is same conductor with different area of cross section or different thickness, means the same conductor is having a smaller or a less thickness at this position and having larger thickness at this position, that means this is having area A2 and here area of cross section is A1. That means its diameter is, suppose here D2 and diameter is D1. Then we can conclude here for same conductor we can conclude that this drift speed, as it is inversely proportional to E, so drift speed at this one, that is suppose Vd1 and here Vd2, as A2 is greater than A1, therefore Vd2 is less than Vd1, because drift speed is inversely proportional to area of cross section. But one thing we have to remember, that if we use same conductor in two different situations with two different diameters, that means suppose this is a conductor having area of cross section, that means this is a diameter D1, area of cross section A1, and of same conductor if we use a piece which is having larger area of cross section, that means larger diameter with the same length and all these things, then you have to remember that for same conductor but in different two situations, this drift speed does not depend on area of cross section or diameter. You have to take into consideration these two different situations, same conductor but with non-uniform nature, and here same conductor with a uniform nature. In both cases, in first case this drift speed depends on area of cross section inversely, and in second case even though there is a difference in area of cross section, but this drift speed does not depend on area of cross section. So this is a drift speed, and which is very important to explain electric current. Now we have to discuss about the important law which is basic of this current electricity, and that is Ohm's law. Scientist Ohm has performed number of experiments by using different conductors at different conditions, that means having different dimensions, different temperature, different material, and he finally concluded that if physical state of conductor remains same, here physical state means its dimensions, its material or nature of material, and third one, and which is very important, that is a temperature. If these things remains constant, same, only at that situation you may say that if physical state of conductor remains same or constant, at that state you may state that the current flowing through conductor is directly proportional to potential applied across it. That means you have to write this in terms of equation as I is directly proportional to V. Generally we state V is directly, most of the students states V is directly proportional to I, but here the important thing is that you have to mention here current is directly proportional to V. And here, as we remove this proportionality sign, we have to place some proportionality constant into V. But here, this proportionality constant is I is equal to G into V, where G is known as conductance. And this conductance is reciprocal of the another property R, that is resistance. And hence this relation will become as I is equal to here V divided by R, and therefore the well-known popular relation is that I into R is equal to V. So this is Ohm's law. From this relation we can define the value of unit of this resistance, that is ohm. R is equal to V by I. So here V is always measured in volt and current is measured in ampere. So volt upon ampere is nothing but resistance R, that is ohm. It is symbolically represented as this. Now we can define what is mean by 1 ohm resistance, or how can we define this 1 ohm resistance? Means if we apply 1 volt potential difference across any conductor and if it produces 1 ampere current in it, then that resistance provided by that conductor is considered to be 1 ohm. Now this is resistance. Now this total experiment can be experimentally studied, and it is graphically studied as if we plot the values of potential difference, different values of potential difference applied across that conductor on x-axis, and the current measured during that is I, then you will get, as there is a direct relation between these two physical quantity, that means you will get graph as straight line passing through origin. As V increases, current also get increased. That means from this graph, if suppose this is angle theta, then you can measure the slope of graph. Slope of graph means ratio of delta I by delta V, and this is reciprocal of resistance. So 1 by R is equal to delta I by delta V. That means if we use 1 by slope, then it will give us delta V upon delta I. And at the same instant, this is nothing but tan of theta. If we take slope, tan of theta is equal to 1 by r, that means ratio of delta I by delta V. So this is relation from this graph for Ohm's law. And but actually in practice there are some limitations to this Ohm's law. This Ohm's law is having certain limitations, out of which one is this Ohm law is not an universal law, means it cannot be applicable for all materials or all conductors. So this is a basic limitation. Now another limitation is that we cannot apply Ohm's law at a higher temperature, because as the temperature increases, means there is a flow of electrons and atoms from that conductor also vibrate largely, and which provides oppose to the flow of electron. So in actual practice, this graph is a straight line up to certain value of temperature, and after that if we increase the potential difference, that means temperature increases and the oppose increases and value of resistance will not remain as a straight line, it changes. So we cannot apply Ohm's law beyond certain limit of potential or beyond certain limit of temperature. And the third important limitation of this Ohm's law is that we cannot apply this Ohm's law for insulators, thermistors, semiconductors. So these are some limitations to this Ohm's law. Now we have to focus on this important physical quantity which is get arised from this Ohm's law, and that is nothing but resistance. So let us focus on resistance. But before that, we have to remember again one thing, that is in accordance with the flow of electric current through any material, we divide material in three categories. One is conductor, another is insulator, and third one is a semiconductor. Conductor is a material in which there is a large flow of electrons, means we get a large amount of current because free electrons are large in number. So these are known as a good conductor, and all metals are considered to be good conductor. Insulator, it is a material through which we cannot flow electric current because there are no any free electrons, and so it is also known as a bad conductor. So wood, glass, these are the example of insulator. Plastic, this is also example of insulator. And finally semiconductor. This semiconductor material is a special type of material because it acts as a bad conductor for normal temperature, and if there is increase in temperature, then it will behave as, or if there is a change in temperature, then it behaves as a conductor. Or by adding some impurity to that material, it behaves as a conductor. So it is having both properties for particular situation. So it is known as, it is not either totally bad conductor or totally a good conductor, but is in between them. So it is known as a semiconductor. So silicon, germanium are the examples of this semiconductor. Now we again come to the point, that is a resistance. So resistance of any material depends on its length, means length of conductor, then area of cross section, and finally its material, means every material, conducting material is having different resistance. So nature of material, area of cross section for that, and length of that conductor, and finally and most important thing is that resistance of any conductor depends on temperature. If we keep temperature constant, and for same material, we can state that this resistance of that conducting material for a given temperature or at given temperature is always directly proportional to its length and inversely proportional to its area of cross section. If we combine these two relations, finally we will get R is directly proportional to L by A. And if we remove this proportionality sign, you will get R is equal to rho into L upon A, where this rho is, as I have stated earlier, that is rho is specific resistance, or it is also known as resistivity. So this is rho. But this rho is, as it is a constant, but it is purely intrinsic property of any material. This is purely a property of material. Means if we keep material same, temperature same, constant, then in that case resistance of that given conductor depends on all these things. So R is equal to rho into L by A. One thing we have to remember, that there are more questions which are based on this concept, which are get asked in CET or NEET exam. That is, there may be change in conductor, or same conductor is changed with a change in length as well as a change in area of cross section at given temperature. Then you have asked about the changed resistance of that material. So now we can determine a relation for that resistance, if that material is get changed, or if we keep same material at same temperature with a different length and different area of cross section. And another thing is to change this resistance is, if we stretch a given conductor, then there is a change in its length as well as area of cross section simultaneously. In that case also the resistance of conductor get changed. Now we mention the relation in these two cases like this. Means if we keep material same and temperature same, if we keep same material and same temperature, these two things are more important. If we keep same material and same temperature, and if we use a conductor with certain length, initially let that length is L1, having area of cross section A1, and this material, as we are not changing material, that means rho remains same. Here we have to remember this thing important, that is specific resistance is constant for that material. So here specific resistance is rho. And if we use another conductor of same material, rho same, different length and different area of cross section, then resistance in both cases is different, and that resistances can be related. As in this first case, we can write resistance as R1, which is equal to rho into L1 by A1, and in another case we can write relation R2, which is equal to rho into L2 upon A2. And if we have to relate these two relations, then we have to use the ratio of these two equations, R1 upon R2. Then it will give rho into L1 upon A1 divided by rho into L2 upon A2. Here rho gets cancelled and you will get L1 upon L2 into A2 upon A1. So this is actually relation for a resistance when we have changed in this way, L1 upon L2 into A2 upon A1. But at the same instant, the same relation can be written in terms of not only directly area, but in terms of its radius also. It can be written as this area of cross section is circular, so its area can be written as A is equal to pi r square. Therefore A1 can be written as pi r1 square and A2 can be written as pi r2 square. So this will become as R1 upon R2 is equal to L1 upon L2 into pi R1 square upon pi R2 square. Here pi gets cancelled and you will finally get another relation. R1 upon R2 is equal to L1 upon L2 into R1 upon R2 whole bracket square. So this is another relation. So all these are the relations for this resistance. And now another thing we have to consider, that if the second condition is if we stretch that resistance wire, means this is a wire, suppose this wire is having length L and area of cross section A, and if we stretch the same wire, now its length is get increased, it will be L2 and its area of cross section will be A2, and that A2 is decreased, means when we stretch the given resistance, stretching the resistance, L1 initial length changes to L2. Relation between them is that L2 is greater than L1, and in that case area of cross section A1 changes to A2, but here A2 is less than A1. In that case we cannot relate this in this form, because area of cross section, whether it is increased or decreased, we have to use another thing, but we have to use same relation, R1 upon R2 is equal to L1 upon L2 into A1 upon A2 upon A1. Because if we have given only the change in length, then the same resistance can be written in terms of length only. For that, as we stretch this conductor, volume remains same. Volume remains same, and therefore V1 is equal to V2. V1 means area into length is equal to area into length, and from this relation we can write A2 upon A1 is equal to A2 upon A1 is equal to L1 upon L2, and if we put this value in this relation, finally we get R1 upon R2 is equal to, here initially L1 upon L2, and for A2 by A1 again we have to write L1 upon L2, so finally you will get L1 upon L2 bracket square. So this is relation when we stretch wire, and this is relation when we change the conductor, when we change the dimensions of a same conductor. So this is a difference between resistances.